Oh, hey. Oh, sorry. Yeah, so here we are. Any questions about anything? Any questions? Could be. Yes, the question is this really the last lecture? And the answer is yes, this is really the last lecture. Hang on a second. Don't look so happy. Well, you always look happy, so okay, I'm not worried about that. What's so funny, Kyle? Okay, well you always look like you think everything's funny. I guess that's cool, you know? I guess it's good to keep our sense of humor in the middle of all this. Like, how do you guys, George, you look relieved? Semester's almost over. Any other questions? Steph? Oh, absolutely. Sure. Yeah. I mean, the question is, can you share the lectures with your friends, the YouTube links, whatever? Absolutely. Maybe we can become signals influencers out there. You know, maybe I can cut some deal with YouTube where I get, you know, a tenth of a penny every time someone watches a minute of one of my lectures. Who knows? That would be really cool. I mean, actually, Amina sent me a still photo of one of the lectures in 2200 on the big screen at her family's house, and I thought that's kind of cool. Like everyone gets to watch a EC 2200 lecture instead of, say, you know, Top Gun or whatever old movies available. But anyway, feel free to share videos and stuff. Anything else? Annie? Yeah, I bet you anything it's going to work out that we have the Prelim 2 grades done before Tuesday, so you can take them into account when you're deciding whether you want to turn the course into SU or keep it as a grade. So we're looking good for that. The TAs have solutions to the 3 problems they're grading. I'm going to grade one of the problems. And yeah, back row Alex. Number 4, that's the one I'm grading. I'm grading number 4, the DFT problem. Okay, so anything else? Anything else before we wrap up this show? Oh, one thing I do want to mention, I just want to give a shout out to all the folks who have loyally shown up to the Zoom sessions. There's a certain subset of the class that has come rather consistently, and I know I'll miss some people, but I can think, like, people run through my head like right away. Michelle, Alicia, Carrie, you've always been there. Maria, of course, and I'm not going to confuse you with Katerina anymore. Don't worry, I'll remember that you're Maria. And Matt and Robert, our West Coast guys. You know, you've gotten up early on a consistent basis and shown up for these. They would be like 8:40 in the morning for you guys. Who else? Amelia, you've been there a few times. Did I say Grace? Grace? Yeah, Grace knows how to use the tablet device that I've had so much trouble manipulating, and she's helped me out with that. So anyway, thanks for showing up and keeping the mornings lively and whatever. That's no knock on anybody else. I know you've got precious things to do with your time, and you know, maybe you're spending your 2200 time watching these videos instead of showing up to the Zoom. That's totally cool. But anyway, okay, so moving right along. Where were we last time? All right. And I'll try to resist going over time. I might even go under time today. Who knows? Because I don't want to like get halfway into something and have to stop. So anyway, we were talking about these essentially IIR systems and the tools that we're using to analyze those. The main topic of the lecture was things like Z-transforms, transfer functions, etc. So I want to get back to this, and we wrapped up the class with an introduction to a really important concept, Fiavio stability, and that's where I'm going to pick it up today. But anyway, okay, so that's the kind of stuff we were talking about. We talked about the Z-transform, and in particular, we talked about a procedure for recovering a signal from its Z-transform, provided the Z-transform was what we call a proper rational function of Z. So we saw how to get x of n, a signal from x of z, when x of z is proper rational. And essentially it involved doing partial fractions, followed by looking up on the table with the canonical examples of z transforms. That was one thing we saw. All right? We also defined the transfer function of a system, a causal LTI system, as the z transform of its impulse response. So if h of n is impulse response of a causal LTI system, we call its z transform capital H of z the system's transfer function. And again, this is something where the book and I talk a slightly different language. The book calls it the system function. I've always thought that was kind of an insipid name for it. I bet you anything, if you took circuits, especially if you took it from Pollack or Molnar, you talked about transfer functions. You didn't talk about system functions. So we're going to use the phrase transfer function to describe that. Okay? And we saw how, for example, using this procedure of getting signals from z transforms, we saw how to find h of z from a difference equation specification of the system. And this works both for FIR systems and for IIR systems, systems that have recursion terms in their difference equation. So it works for both FIR and IIR systems, okay? And we talked about finding the output corresponding to a given input by taking the z transform of the input, multiplying it by the transfer function, taking the inverse z transform of that to get the output. That was based on things like the time shift rule or the time delay rule and the convolution rule for z transforms. That was all last time. At the very end of class last time we introduced this concept called BIBO stability. And a system, an LTI system, a causal LTI system, we're only considering causal systems here, essentially. Causal LTI system is BIBO stable when every bounded input signal x of n gives rise to a bounded output signal. And remember what bounded means? This is important. Bounded is about the values of the signal. It's not about the time duration of the signal. So time duration is about this. Bounded is about this, about how big the signal gets, right? And if you have a signal, all of whose values stay under some fixed ceiling and above some fixed floor, then the output is also going to have that property that is bounded when you have a BIBO stable system. And some people call it BIBO stable. I call it BIBO stable. BIBO will not get you laughed out of the room like fur, you know, like I said last time. We were going through our example systems, some of the example systems we dealt with the whole semester, like, for example, the zero system, the identity system, the pure N1 shift system, the causal sliding window M-fold averager system. We saw that all of those, whoops, hang on a sec. I got a little too violent with my pen here. We saw that all those were BIBO stable. So saw that a bunch of our example systems were BIBO stable. And at the very end of class last time, I was about to talk about the Discrete-Time Integrator. And that's the first example of a rather innocent-looking system that's not BIBO stable. So let's look now at the Discrete-Time Integrator. And remember what that system was? when you have an input signal x of n, y of n is equal to the sum of all the previous values of x of n. So this is the way we wrote it down. Y of n equals the sum from k equals 0 to infinity, y of n minus k for input signals x of n. If you restrict your attention to signals in the universe where x of n is 0 for n less than 0, still works. Okay, but anyway, the question, is this BIBO stable? How many people think it is? I mean, obviously it's not, because I wouldn't be asking this rhetorical question if it's not. So how many people think it is BIBO stable? Come on, somebody be contrarian. No? Nobody? Nobody? All right. Well, you're all right. No. How many abstain? Everybody. Fine. Whatever. This is not BIBO stable. Okay? And let's check on an input signal that is in our universe of signals that are 0 for n less than 0. So this isn't BIBO stable. Okay? So let's look at a signal x of n. So consider the input signal x of n equals, how about 3u of n? So that's equal to 1 when n is bigger than, or sorry, 3 when n is bigger than or equal to 0, and 0 when n is less than 0. Let's put that into the system and see what comes out. Okay? Now, we've done this before with the system. You find that this x of n is bounded. Okay? This x of n is a bounded signal, right? Just want to make sure everyone understands what a bounded signal is. Alex, not? Yeah, okay, again. X of n has infinite duration, right? It lasts forever. It never turns off, but it has values that lie underneath a ceiling and above a floor. Okay, this is bounded. It's not infinite duration, but the values are all less than or equal to 3. The absolute value of all the values are all less than or equal to 3. That's what bounded means, okay? So I think you get what I mean, but you asked it in a questioning kind of way. So once again, please try not to be confused between finite duration and bounded. Okay, those are two things that people mess up all the time. But anyway, this x of n is bounded. What is the output signal? The output signal to which it gives rise is what? What happens when I put this signal into the discrete-time integrator? Well, what is the value of the output signal for n less than 0? Critic. Yes, 0, of course. It's 0 when n is less than 0. Because why? Because when n is less than 0, you're summing up all the previous values of the input signal, and it's all zeros when n is less than 0. But as soon as n hits 0 and goes beyond, you're summing up 3s, okay? And it turns out to be equal to 3 times n plus 1 when n is bigger than or equal to 0. So, step goes in, ramp comes out. A ramp that goes up to heaven without slacking is not a bounded signal. So this is not a bounded signal. So the conclusion is that this system is not BIBO stable. We have produced a bounded input signal that gives rise to an output signal that's not bounded. All right. Now, last time we proved quickly, but anyway, I mentioned last time. So we quote unquote proved last time that BIBO stability is equivalent to absolute summability of the impulse response. So H is what we call an L1 signal. L1, that's just signal talk. Okay, you're going to see that in the future. Hang on to it. All right? And when the system has a proper rational transfer function, as all the systems, all the IR systems in this course, and the FIR systems as well do, BIBO stability has a simple characterization in terms of the poles of the transfer function. All the poles, and remember, what are the poles? The poles are the roots of the denominator polynomial. The transfer function is proper rational. Its numerator is a polynomial, its denominator is a polynomial. They have roots. Express it in lowest terms. The roots of the denominator polynomial are all the poles. All the poles of h of z are inside the open unit disk. So they're in the region magnitude of z less than 1 in the complex plane. Okay? All right. Let's check these two criteria for the system we just showed was not Fiavio stable, the discrete time integrator. So e.g., for the discrete time integrator, h of n is what? We discovered this earlier in the course. H of n is just the unit step. The impulse response of the discrete time integrator is a unit step. And this is not an absolutely summable signal. If you try to sum that from 0 to infinity, it's 1 plus 1 plus 1 plus 1 goes to infinity. So it's not an L1 signal. All right? What about the transfer function of this system? What is h of z? H of z is the z transform of a unit step. That was the second example of the z transform that we did. And we discovered that the z transform of a unit step written my way in terms of z's as opposed to z inverses is z over z minus 1. The only pole of this transfer function is z equals 1. So z equals 1 is the only pole, not in the required region for BIBO stability. It's right on the unit circle as opposed to strictly inside, and that's where the poles have to be for BIBO stability. Okay? All right. What about BIBO stability for FIR systems? Last time, I think I kind of tossed off, off the side. Oh, by the way, every causal FIR system is BIBO stable. But they are, and it's really easy to see. Okay, so as for causal FIR systems, on which we've spent so much time this semester, they're all BIBO stable. And you can see this in at least 3 different ways. All right. All right, what are the 3 ways? One way is just using the definition of BIBO stability. So using definition of BIBO stability. Suppose your system is specified by the difference equation y of n. So say the system is this, y of n equals the sum from k equals 0 to m bk x of n minus k. That's your generic garden variety causal FIR system. If x of n is bounded, say less than or equal to some r, let's call it r1 for all n, then absolute value of y of n is going to be less than or equal to the sum, the absolute value of the sum from, or it's equal to this, sum from k equals 0 to m of bk x of n minus k. That's less than or equal to the sum from k equals 0 to m, absolute value bk times r1. and that's equal to this. And I can call this number R2. Bottom line, if X is a bounded input signal, that's the same thing as saying there's an R1 for it. That X of n is less than or equal to R1 for some positive number R1, then Y is also bounded. It has an R2, i.e. X of n bounded implies that Y then is also bounded. QED. Okay, that's using the definition of Fiavio stability. We've proven that every FIR system is Fiavio stable. Every causal FIR system is Fiavio stable. What's another way to show this? Fiavio stability is equivalent to absolute summability, or L1-ness, if you will, of the impulse response. So for that system, causal FIR system as above, so governed by the difference equation above. The impulse response is just given by the B's. It's 0 when n is less than 0, and it's B sub n when n is between 0 and cap m, okay? And it's 0 when n is bigger than cap m, okay? This is an L1 signal. It's trivially absolutely summable. Sum from n equals 0 to infinity, absolute value of h of n, is just the sum from n equals 0 to cap m of absolute value of b sub n, and that's finite. So h is an L1 signal, and the system is Fiavio stable by our L1 impulse response criterion. Okay, so another QED, second method showing that every causal FIR system is Fiavio stable. Finally, guess what criterion we're going to use now? Okay, Brendan. Yeah, we're going to use the poles of the transfer function thing. Okay, we're going to find the transfer function. So, what is the transfer function of the system above? We actually found this last time. For an FIR system, it's going to be this. It's going to be h of z, cap h of z is equal to the sum from k equals 0 to m of bk, z to the minus k. And we could do bn, z to the minus n if you wanted to, whatever. And you can leave it this way. This is the customary way of leaving the transfer function for an FIR system, but you can also write it this way. You can also write it as denominator of z to the m, and in the numerator you have the sum from k equals 0 to m of bk z to the m minus k. Okay? That's the way I like to write transfer functions, z transforms, whatever, as ratios of polynomials in z. What are the poles of this function? Assuming that 0 is not a root of the numerator. Come on. Somebody. Aditi. Yes, very good. They are all 0. The poles of this guy, the only pole in it, it's a higher order pole. It's not a first order pole, as they would say in systems parlance. The only pole of this, of h of z, is z equals 0. And clearly because z0 is less than 1 in magnitude, this is in the allowed zone. Thus, all poles satisfy magnitude less than 1, which implies that the system is Fiavio stable. All right. So those are three different ways of seeing that a causal FIR system is Fiavio stable. Everybody got that? All right, very good. So what's something else we can do? Fiavio stable systems are the kind that you want to be building in real life. Okay, you don't want to build things that aren't stable. And anyway, what do we use these systems for? We use them for lots of things, but we use them as, and why do people call them filters, even though we haven't even talked about frequency yet? What we need to do now is we need to talk about frequency response of these systems, these more general systems, these IR systems, these systems with proper rational transfer functions. And to do that, what we have to do is we have to back away, in a sense, from the universe of signals that we've been dealing with for the last 3 lectures or so, where all the signals have 0 values for n less than 0. So okay, let's see if I hope I didn't mix you up too much by saying all that stuff. So the next topic for these systems is frequency response of these kinds of systems, of general systems with proper rational transfer functions and this includes, of course, all the causal FIR systems. And I want to say general causal systems here. General causal systems with proper rational transfer function, and includes all causal FIR systems. And just to preview, what we're going to find is, we're going to find that if a system with a proper rational transfer function is Fiavio stable, then it has a frequency response. And we're also going to find that there is, like there was for FIR systems, a whole notion of transient and steady-state response to sinusoidal inputs for these systems. That comes out a little different, but it's quite similar. Okay, so the first thing to note, recall that for any FIR system, or for any LTI system, that an LTI system with impulse response h of n has a frequency response h hat of omega hat given by the DTFT formula. H hat of omega hat equals the sum, and again we're talking about a causal, so we're going to talk about sum from n equals 0 to infinity, and eventually n equals minus infinity to infinity, h of n e to the minus j n omega hat, which is the sum from n equals 0 to infinity, h of n e to the minus j n omega hat, and this is because causal. And this is just the analysis equation for the DTFT, saying that the DTFT of the impulse response is the frequency response, provided that this thing exists. Okay, like e.g. sum converges. Okay, so provided you have a DTFT for the impulse response, that's when we say the system has a frequency response. All right, now I claim that if you have a BIBO stable system, then you have a frequency response. This sum converges, h of n has a DTFT. So here's a fact. Fact is the following, that if h of n is the impulse response of a causal LTI system, causal BIBO stable LTI system, then h of n has the dTFT, h hat of omega hat, and the system therefore has the frequency response. Okay, why? Why is that true? You look at the analysis equation, the dTFT analysis equation. So why? Why? By the way, whenever we have fact or theorem or whatever, and I say why, or how does this go, or to see this, those are all euphemisms for the word proof, okay? So why is like a really short three-letter euphemism with a question mark for the word proof. So why? Why is this the case? Consider the analysis equation. H hat of omega hat equals the sum from n equals 0 to infinity. And again, it starts at 0 because the system is causal, therefore h of n is 0 5 less than 0. H of n e to the minus j n omega hat. This series converges for all omega hat because h of n is an L1 signal. Namely, this equation, this inequality holds. That the sum from n equals 0 to infinity of the absolute value of h of n converges. And that follows, in turn, from BIBO stability. Okay? If you take the absolute value or magnitude of the sum of h of n e to the minus j n omega hat, that's less than or equal to the sum of the absolute values or magnitudes of the terms. The e to the minus j n omega hat contributes nothing. You get the sum of the h of n magnitudes. Boom. It converges for all omega hat. Okay? So every BIBO stable system has a frequency response. So here's the big result here. BIBO stable implies has a frequency, a well-defined frequency response. Okay? That's one thing. And when you have a frequency response, you know that when you put e to the j n omega 0 hat into the system, you know, and as usual, as always, we're going to have this. If I put e to the j n omega 0 hat into the system, what's going to come out is h hat of omega 0 hat, e to the j n omega 0 hat. You had a bunch of this stuff on prelim 2, a lot of homework problems. This is the thing I call using the picture or whatever. But anyway, that's the case, all right? Question. Okay, very good. Jack, see you air Jack, by the way, asked the following question. Is the converse true? If a system has a well-defined frequency response, is it necessarily BIBO stable? Good question. How many people think it is? How many people think not? How many people abstain? Actually, this is like the most even vote we've ever had, which proves that you guys are learning stuff because, you know, it's almost true. The converse is almost true, but not quite, okay? So what about the converse? So let me put this in parentheses. This is a fine point, but, you know, Jack, fine, you raised it. It's good to think about. The converse is almost but not quite true. So the converse is almost but not quite true. In other words, there are systems that have well-defined frequency responses that are not BIBO stable. Okay? So consider, for example, ideal low-pass filter. Remember what the frequency response of that was. It looked something like this. So this is omega hat B, say. And this is plus or minus pi, 1. This is our h hat of omega hat. And over here in the time domain, we have h of n is going to be like a sinc kind of thing. So it's sine of n omega 0 hat over pi n. All right? This is a well-defined frequency response. This is not an L1 signal. And one way to see that is that the terms only go to 0 like 1 over n. And that's not fast enough to make the absolute values of them sum up, unfortunately. So the system is not Fiavio stable, even though it has a well-defined frequency response. And if you want to know, like one thing you can take this one to the bank. Again, I think I said that twice today, or maybe last time and today, I forget. But if a system is Fiavio stable, its frequency response can't have any jumps. And this ideal low-pass filter frequency response jumps from 0 to 1 and then back down again. So that's not allowed. When you have a Fiavio stable system, the frequency response turns out has to be a continuous function of omega hat. So if you ever see a jump in a frequency response, like for example ideal high pass, ideal band pass, boom, they are not Fiavio stable either. Okay, but anyway, that's a fine point. Good, I'm glad you raised it. Okay. What about, so a Fiavio stable system has a frequency response. It's the DTFT of the impulse response, as always. What if a system has a proper rational transfer function? Okay. Is there some way of writing the frequency response in terms of the transfer function? So how about when a Fiavio stable system has a proper rational transfer function? And by the way, back to the question about the converse of this. It turns out that a system with a proper rational transfer function has a frequency response if and only if the system is Fiavio stable. So the converse is true in the limited range of systems that have proper rational transfer functions. The ideal low pass, high pass, and all those filters don't. Okay, so, but anyway, when a Fiavio stable system has a proper rational transfer function, okay, say h of z, what do we know? Well, we know that all the poles of h of z, because of Fiavio stability, have to lie inside the unit circle. So we know that all the poles of h of z lie in magnitude of z less than 1. In particular, there are no poles of h of z on the unit circle. So in particular, there's no poles of h of z on the unit circle. Okay? Now, what does it mean to have no poles of h of z on the unit circle? It means that you can plug in e to the j omega hat for z, and it's not going to blow up. So thus, we can plug in z equals e to the j omega hat in h of z, and it won't blow up. Okay, that's one thing we know, right? Now, it also won't blow up if h of z has poles outside the unit circle, just as long as they're not on the unit circle. But still, let's not worry about that for the moment. So moreover, by definition of h of z as the z transform of the impulse response, we have h of z is equal to the sum from n equals 0 to infinity. And again, the n equals 0 is because causal. H of n, z to the minus n. Okay? Now, what happens if you plug in e to the j omega hat for z? So plug in e to the j omega hat for z, as we know we may. On the left-hand side, we get h of e to the j omega hat. On the right-hand side, we get the sum from n equals 0 to infinity of h of n, e to the j omega hat to the minus n, e to the minus j n omega hat. And lo and behold, what's that? That is the formula, that is the analysis equation for the dTft of h of n, i.e. this is the frequency response, h hat of omega hat. Okay, so finally, we get to reconcile my notation for h hat omega hat with the book's notation. And it goes like this. So bottom line, a BIBO stable system with proper rational transfer function. And again, we're talking causal here. I wish I didn't have to keep saying causal, but I do. Causal BIBO stable with proper rational transfer function h of z has a frequency response h hat of omega hat given by the following equation. H hat of omega hat equals h of e to the j omega hat, which is just h of z evaluated at z equals e to the j omega hat. And this is where the notation h of e to the j omega hat comes in for what I've been calling h hat of omega hat. Now why don't I like to use h of e to the j omega hat from the beginning? Because I think of the frequency response first off as a function of omega hat, not as a function of e to the j omega hat. Second of all, this is only really true when you have a transfer function that's a quote-unquote nice function of z, including, say, proper rational transfer function. If the transfer function is not a quote-unquote nice function of z, it's not quite that way. So, and also systems, there are systems that have frequency responses that don't even have transfer functions because their impulse responses don't have z transforms. There's just so many reasons not to use this notation that the book uses that I don't use it, but this is where my notation meets the book's notation. Okay, so there you go. All right, let me check the time here. Okay, we've got a reasonable amount of time left. Not as much as I wish, because, okay, wish I could cover some more stuff. All right, so I told you that now that we know how frequency responses work for these more general systems, IIR systems included, that are BIBO stable, I said that there's going to be something about transient and steady state, and sure enough, there is. Okay. So it turns out we have a notion of transient and steady state responses of causal BIBO stable systems. You have to be BIBO stable systems. To sinusoidal inputs starting at time 0. And remember, those are the ones we talked about those for FIR systems, in terms of transient steady state. So let's see what's going on for these more general systems. All right. And what I'm going to do is focus specifically on those that have proper rational transfer functions. It turns out you can do this for other BIBO stable systems, but let's assume, just for the sake of exposition, the system has a proper rational transfer function h of z. And suppose that h of z has a bunch of poles, right? Say z1 through z cap n. So say h of z has poles z1 up through z cap n, right? What does BIBO stability tell me about those poles? Yes, they all have magnitude less than 1. zk has magnitude strictly less than 1 for k between 1 and n by Fiavio stability. Okay, my computer is giving me an alarm here. Let me hang on, let me just check this. Problem with audio capture. The video is not being recorded. Or the audio, no audio is being recorded. Check the built-in microphone. Well, let's see. I mean, the microphone is, the green thing is going like it always does. Can you hear me? I sure hope you can, because I don't want to give this lecture all over again. All right. Okay. All right. Testing, check, 1, 2, whatever. Maybe I just shut up for too long. I don't know. Okay. All right, so anyway, all the poles have magnitude less than 1. All right? Great. Suppose I drive the system with, so let's use as input signal x of n is equal to, say, e to the j n omega 0 hat times u of n. Okay, instead of having just plain e to the j n omega 0 hat, let's do e to the j n omega 0 hat starting at time 0. Okay, so now you've got your suddenly appearing sinusoid input. Let's put that into the system. What comes out? So let's figure out the resulting y of n using, guess what tool? Z transforms. How do we do that? Okay, first we take the z transform of x of n. So x of z turns out to be equal to, this is one of our canonical examples. Remember, x of n equals z0 to the n u of n. Gave us z transform z over z minus z0. So this comes out to be z over z minus e to the j omega 0 hat. Okay? And that's because x of n is of the form z0 to the n u of n with z0 equal to e to the j omega 0 hat. Okay? That's the z transform of x. What is the z transform of y? Y of z is always h of z, x of z, when x has the z transform. Okay? And this is h of z times z over z minus e to the j omega 0 hat. All right? Now let's figure out y of n. Let's figure out y of n. How do we figure out y of n? We use the partial fractions and lookup drill, right? You do partial fractions by Zen, by MATLAB, whatever method you want to use. So find y of n using partial fractions plus the table. Okay, so what happens when you partial fractionify to make up a new verb? This y of z over z. So if you expand y of z over z in partial fractions, it's going to come out to be, well, there's going to be a term over z minus e to the j omega 0 hat, and the numerator of that term is going to be h of e to the j omega 0 hat. Because the way you figure out the numerator is you plug in, you just multiply by z minus the pole, and you plug in the value of the pole into what's left. And then you're going to have like the sum from k equals 1 to cap n of some ck's divided by z minus zk's. And this, of course, assuming that you don't have any repeated roots. A little more complicated in that case, but nothing to write home about. So that means that y of z itself is equal to h of e to the j omega 0 hat times z over z minus e to the j omega 0 hat plus sum from k equals 1 to cap n of ckz over z minus zk. All right. Now, when you go back to the time domain using the table, now we're done with the partial fractions part of the recipe. Now we use the table to go back, and we get this. We get y of n, so this is by table. Y of n is equal to z over z minus e to the j omega 0 hat. That just goes back to e to the j omega 0 hat u of n. So this is h of e to the j omega 0 hat times e to the j n omega 0 hat u of n plus, and these other terms go back to ck zk to the n u of n. All right? Now, because of BIBO stability, all of the zk's, all of the poles of h of n, or of h of z, are less than 1 in magnitude. Thus, every term in this expansion, in the second term here, goes to 0 as n goes to infinity. So this goes to 0 as n goes to infinity because magnitude of zk is less than 1. 1 less than k less than equal to n. That's something we mentioned up there. This, on the other hand, for all n, for all large n, for all n bigger than or equal to 0, it's the same as h of e to the j omega 0 hat times e to the j n omega 0 hat. And that is the output signal we would have gotten had we driven the system with a forever sinusoid. Instead of e to the j n omega hat starting at n equals 0, we run it forever. Okay? So this is the same as quote-unquote forever sinusoid output. All right, so what is the big picture here? The big picture is, i.e., y of n is equal to a steady state term that looks like the response to a forever sinusoid. So it's going to be h hat of omega 0 hat, j n omega 0 hat, u of n, plus a transient term, something that goes to 0 as n goes to infinity. Okay, and by the way, I used, to get this, that h hat of omega 0 hat equals h of e to the j omega 0 hat here. Okay. All right, so transient term. Now, excuse me, unlike the FIR situation, we don't have a transient epoch that starts and ends and followed by a steady state epoch where the thing looks exactly the same as it would have looked had you driven it with a forever cosine. In this case, the transient is always there, but it's dying out, okay? So you never hit steady state, you approach it. All right, so contrast to the FIR situation, the transient never disappears completely. Okay, the system asymptotically approaches steady state. Okay, so that's what's different about the FIR system. And this probably looks a little more like transient and steady state stuff that you saw, say, in the circuits class, where you drive the system with a cosine that starts at time 0. You're going to have some transients. The transients are going to be like e to the minus t over rc things, right? Tau is like the time constant. And those are going to die exponentially as t goes to infinity, leaving behind the sinusoid, right, which is the steady state response. But the transient never disappears 100%. And the same thing happens here in discrete time. Okay. Let me check the clock. All right, so we have this transient plus steady state idea. Now, I want to wrap up by considering, clearly we can't do much more in the roughly 17 minutes that remain, but maybe 20 minutes. But we can do some. So let me just talk a little bit now about designing filters of various kinds using Z-transform / transfer function / pole zero kinds of ideas. All right. So what I want to do is I want to wrap up with a brief discussion, and we're actually going to get to revisit a problem that we talked about earlier in the semester of the basics of designing filters, i.e. frequency responses, essentially, because that's what a filter is. It's frequency responses. Designing frequency responses to do various things, okay? To do various things. All right, so what kind of things might you want a frequency response to do? You might want it to kill a cosine. We talked about that. You want it to kill 3 different cosines. We talked about that. Or you might want something that's like a good low-pass filter or a good band-pass filter or something like that. So you're designing frequency responses to do various things using the circle of ideas involving poles, zeros, transfer functions, etc. And again, I always hesitate when I write down the word zeros. Should it have an E? Should it not have an E? So I'm writing it like zeros, like the Greek surname. But anyway, poles, zeros, transfer functions, etc. Okay, first thing I want to note is that if someone comes up to an whole plaza with a proper rational transfer function and said, actually whole plaza is more like in that direction. So if someone comes up to a whole plaza with a proper rational transfer function and says, please build me a system that has this transfer function, what would you do? Well, it turns out you can easily move from a proper rational transfer function to a difference equation. And you can easily implement a difference equation on a computer or using a block diagram, like in the handout. You're going to get a handout that has, in fact, the handout is already there. It has a section on block diagrams, which is something I just didn't feel like spending lecture time on. So first thing to note, first observe that given a proper rational, and I'll just do one quick example, h of z, it's easy to write a difference equation governing a system with that h of z as its transfer function. And all you have to do, essentially, is reverse the process that we followed earlier to get from the difference equation to the transfer function. For example, suppose, say, h of z is equal to, say, z squared minus 7z plus 11, I don't know, divided by z squared minus 13z, or plus 13z minus 19, say. Someone comes up to a whole plaza and says, here's a transfer function. I want a difference equation that governs a system that has this as its transfer function, because I know how to build a difference equation in a computer. I can write Python code for it, whatever. So this is what you do. First, you go back to the Z-inverse version of this, the version that everyone likes to use for Z-transforms. So first you Z-inverseify h of z. So that becomes 1 minus 7z inverse plus 11z to the minus 2. divided by 1 plus 13 z inverse minus 19 z to the minus 2. And then you use y of z equals h of z x of z. And you get this. You get y of z equals that thing, 1 minus 7z inverse plus 11z to the minus 2 divided by 1 plus 13z inverse minus 19z to the minus 2, x of z. That's the same thing as saying 1 plus 13z inverse minus 19z to the minus 2 y of z is equal to 1 minus 7z inverse plus 11z to the minus 2 times x of z. Always takes longer to do an example than you think it's going to take. By the time delay rule, this corresponds in the time domain. So the time delay rule for z transforms. In the time domain, this becomes y of n plus 13 y of n minus 1 minus 19 y of n minus 2 is equal to x of n minus 7 x of n minus 1 plus 11 x of n minus 2. And there's your difference equation. And if you want, you can write it in the standard way. Y of n is equal to minus 13 y of n minus 1 plus 19 y of n minus 2 plus x of n minus 7 x of n minus 1. And this is your final answer, plus 11 x of n minus 2. Boom. There you go. All right. So that's how you move from transfer function to difference equation. All right. That's thing number one. Thing number two is, if I know the poles and zeros of h of z, if h of z is a proper rational function, I know the poles and zeros. The zeros are the roots of the numerator. If I know the poles and zeros of h of z, then I know h of z up to a multiplicative constant. Okay. So next, observe that knowing poles and zeros of a proper rational h of z entails knowing h of z up to a multiplicative numerical constant. So knowing h of z up to a constant multiplier. I really hope the sound is recording in this lecture, actually. Now the green thing, there it goes, okay. All right, so knowing the poles and the zeros is the same as knowing h of z up to a constant multiplier. So in some sense, knowing the poles and zeros of a system's transfer function, when you know the system has a proper rational transfer function, tells you essentially everything about the system. So people talk about systems as in one-to-one correspondence as pole zero locations. So in this way, essentially we've got systems, at least causal LTI systems with proper rational transfer function, in one-to-one correspondence with pole zero plots. Okay? So you go on the complex plane and you put a little circle where there's a zero, a little x where there's a pole, whatever. Okay. Now, to design filters, what you're looking for is BIBO stable systems that have frequency responses that satisfy various criteria. So, designing filters using these pole zero kinds of ideas, your goal is always going to be some BIBO stable system, so a BIBO stable system, all right, whose frequency response has some desired properties. So with a desirable, so to speak, frequency response, h hat of omega hat, which of course is e to the j omega hat when the system has a proper rational transfer function. So this is because proper rational h of z. All right. So designing it to be Fiavio stable means that you've got to have poles inside the unit circle. You can have zeros anywhere you want, but you've got to have poles inside the unit circle. So stability requires poles inside the unit circle, so in magnitude of z less than 1, that zone in the complex plane, but the zeros can be anywhere you want. Okay? Now, what happens when you get close to a pole of a transfer function? It starts to blow up, right? What happens when you hit a zero of a transfer function? It's equal to 0. So what I want to do is I just want to revisit briefly. Sorry to be nervously looking at the time here. I want to revisit. There's a lot of stuff about this in the book. You know, it's kind of at loose ends, and I wanted to spend time talking about the pole locations of generalized linear phase FIR filters. I'm just not going to have time to do that. But I want to revisit, for the final thing, revisit a problem we saw before, the quote-unquote kill one cosine problem. Okay? So, the FIR way to do it, to kill cosine of n omega 0 hat, is this. We had this before. Y of n is equal to x of n minus 2 cosine omega 0 hat, x of n minus 1 plus x of n minus 2. So that was something we derived before during the semester. Okay? Now, if you take the transfer function of this system, you will find that it has zeros the system's transfer function, and this is something that's easy to do in the comfort of your own quarantine. Okay, the system's transfer function has zeros. I spelled zeros with an e. Zeros at z equals e to the plus and minus j omega 0 hat, and it has pole at z equals 0. So if you did a pole 0 plot, this is what it would look like. Okay, so these are the zeros, the zeros. This is e to the j omega 0 hat, e to the minus j omega 0 hat, and then you put a double pole so that it indicated with a 2 there. All right, you'll find that's to be true. Now, I mentioned that when we talked about this FIR way of doing it, I said that this is going to not only kill the cosine of frequency omega 0 hat, but it's going to mess crazily with all the other cosines as well. Okay? How can you make an IIR system, a system that's more complex perhaps, that both kills the cosine of omega 0 hat and does not do too much damage to other cosines, at least magnitude-wise? Okay? So you can come up with a more complicated, so here's an IIR modification of this. That still kills frequency omega 0 hat, but doesn't mess up other frequencies so much, okay? At least magnitude-wise. You design a filter that has those same zeros. And remember, we're thinking here, systems, 1-to-1 corresponds with pole 0 plot. Same zeros, zeros, so e to the j omega 0 hat, e to the minus j omega 0 hat, so the same zeros. And now we're going to throw in a couple poles. Where are we going to throw them in? We're going to throw them in nearby the zeros, but still in a zone that makes for a Fiavio stable system. So we're going to put a pole here and a pole here. What are these poles? Those poles are going to be rho e to the plus and minus j omega 0 hat, where rho is less than 1 but almost equal to 1. So nearby, quote-unquote, stable poles. And stable, what I mean by that is that they're inside the inner circle. Now, why does this thing still kill e to the j omega 0 hat? You figure out the transfer function. Transfer function comes out to be h hat, or h of z is equal to z minus e to the j omega 0 hat, z minus e to the minus j omega 0 hat, divided by z minus rho e to the j omega 0 hat. Z minus rho e to the minus j omega 0 hat. All right, what is the frequency response? H hat of omega 0 hat is equal to h of e to the j omega 0 hat equals 0. Same thing for minus omega 0 hat. So it still kills cosine of n omega 0 hat. But the nearby poles make it so that the nearby stable poles, I almost put poles, P-O-L-L-S. Yeah, right. Let's not even talk about elections. Nearby stable poles make h hat of omega 0 hat, which is, of course, h of e to the j omega 0 hat. The magnitude of that close to 1 for other omega hat values not equal to omega 0 hat. And you can just sort of figure that out because the magnitude of these numerator and denominator terms, when you plug in z equals e to the j omega hat, are going to be close to each other. Okay? So this means, i.e., the system, it's a more sophisticated, it's a more complex system than the FIR solution to killing the cosine. The system doesn't attenuate or amplify other frequency cosines in any kind of a radical way. It might phase shift them crazily, but whatever. System, at least magnitude-wise, doesn't mess significantly with other cosines, other sinusoids. And you can go on using the stuff in the book, like say I want a low-pass filter, that's going to mean I want my zeros to be around on the left side of the unit circle, my poles to be here or there, whatever. There are filter design software things that design various kinds of filters. You have a whole classes of filters, elliptical filters, Chebyshev filters, whatever. Used to be that whole DSP courses were devoted to this stuff, but now it's all automated. So, people don't really talk about this stuff anymore in an academic way. I would love to talk about that stuff, but unfortunately, we have reached the end of this last lecture in EC 2200, and I just want to say, to wrap things up, that I really enjoyed your company for the 6 or 7 weeks that we got to spend together. I got to learn a little bit about all of you, teeny bit about all of you, and a little more about some others. And I really have been spending all these lecture times imagining you out there and where you used to sit and all that kind of stuff. So anyway, thanks for hanging in there, and congratulations. We're almost through this really unusual experience that we can tell our descendants about. And I guess that's all for now. So I will hereby, for one last time, tell you I miss you guys, and I can't wait to see you in the fall.